Well, welcome back to Chapter 19. We are going to revisit some reductions, specifically reducing a carbonyl all the way off, as in the Wolfe Kitchener. But let's start, as usual, with kind of a where are we? We are actually towards the end of Chapter 19, because we've been kind of skipping around in this chapter. So a little review, a little new stuff. This mini lecture focuses only on the reduction of the CO double bond. Alright, well, we've already seen the Wolfe Kitchener, so why are we looking at it again? Well, it's a good review. You remember that we were introduced to it because back in, I think it was chapter 17, it told us a little bit about making hydrozones, making imines, shift bases, and hydrozones. So the Wolfe Kitchener works because we have hydrazine making this intermediate hydrazone, which then allows for the formation of a negative charge, and under basic conditions we eventually lose nitrogen, the carbanion gets protonated, yada yada yada. So that's why we learned about it before. So it's a great way to reduce carbonyls. However, it's very harsh, and it's clearly under strongly basic conditions. It's sodium hydroxide and heat. So, will the Wolfe Kitchener, or Kitchener-Wolfe, work in this particular case? And I hope the answer you would give me is, oops, no, because under these conditions, particularly when I have NaOH present in plenty of energy, I'm going to boot off that chloride, and I'm either going to get substitution or elimination there. So the Wolfe Kitchener would be a bad choice in this particular example. So that is why we learn about some other ways to reduce off the CO, reduce the double bond down to the CH2. Alright, so let's say I have this wacky looking molecule here, and I want to reduce those two ketones, that diketone, all the way down to that perfectly boring alkane, although it's kind of a pretty three-dimensional structure. How can I do that? Well, the Clemmensen is a way that you can do that. It uses what's known as a zinc amalgam. So right here I've dissolved zinc metal in a solvent. The solvent is liquid mercury. So that's an amalgam. And when I treat my diketone with the zinc amalgam, what I eventually do is end up making carbon-zinc bonds. The mechanism is not something we need to focus on. I'm just giving you a little bit more information so that you can see that this looks a lot like, I hope, a C-. It's another organometallic. It just happens to be an organozinc. So, since the polarity of an organometallic basically puts a negative onto the carbon, when I add HCl, I protonate to make my alkane. So the Clemmensen works well, but it is harsh and strongly acidic. So again, I say, will the Clemmensen reduction work for this example? And again, I hope you say, oops, no, because clearly I have a double bond there, and in the presence of HCl, of course, electrophilic addition would take place, and my double bond would be gone. It would react with the HCl to make the chloride. So in this particular example, I could use the Wolfe Kitchener. Alright, they're both pretty harsh though. So there's one more choice, and that is to use Raney nickel. So Raney nickel is a very conveniently mild way to reduce a carbonyl down to the alkane. And you can see how mild this must be if I carry out this reaction in the presence of an epoxide right here, and the epoxide is untouched. So that's pretty wild, and pretty mild too. How does this work? Well, it works by converting my carbonyl into a thioacetal. That's supposed to be an H there. So that thioacetal then reacts, totally magic chemistry here, reacts with Raney nickel. It's just a special form of metallic nickel, and that replaces this whole piece with the two hydrogens that make up your alkane. Nice mild reaction. So let's look at the example below. I ask you, will this reaction work? Well, it's super mild, right? But it won't work. Why not? It won't work because which is more reactive, the aldehyde or the ketone? And the aldehyde, of course, is more reactive. So when I try to make my thioacetal, it's going to react here. So bottom line is, even the Raney nickel method isn't going to work for all examples. In fact, this example is going to be a problem no matter what method you use, because I cannot reduce my aldehyde I cannot reduce my ketone in the presence of the more reactive aldehyde. That's going to require magic. Or it's going to require something special called protecting groups, which is the subject of the next mini lecture. So to summarize, you have three ways to go from a CO double bond to CH2. The Wolfe Kitchener via the hydrazone under strongly basic conditions gives you the alkane. The Clemmensen under strongly acidic conditions makes an organozinc intermediate, which is protonated by the HCl to give you the alkane. Or the Raney nickel, which makes the thioacetal, and under some kind of bizarre magic chemistry that we don't even talk about, reduces that thioketal down to the alkane. So three choices. Just think about the conditions. Sometimes the conditions, you can use any one of them, but sometimes it will make specific sense to use one of these methods over the other. All right, so speaking of protecting groups, let's make this. How would you make this? Well, I think I would make that by using my alcohol disconnection, pushing it back in there, breaking that off as a Grignard. Yeah, I like that idea. Let's try that. Whoa! Let's not try that. Let's save this for the next mini lecture and see what we can do synthesis-wise for that crazy problem in that mini lecture. See you in class.